Hello students, welcome to the course on Advanced Communication Systems and the course code is ece801. This is a 3 credit course for BTech 8 semester EC students. Myself, Dr. Surojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata, and this is my official email address. Now, in the last two classes, we have started module number 5, that is statistical multipath channel models. We have discussed about time varying channel impulse response, narrowband model, fading model, and wideband fading models. Now today we are going to start with the topic of power delay profile from the wideband fading model, that is power delay profile, coherence bandwidth, discrete time model, and spatio-temporal models, with the lesson objective of to find the statistical characteristics of large-scale propagation. And this topic is mapped with CO number 2. So let us start lecture number 3 from the module 5, that is statistical multipath channel models, with the topic of power delay profile. Now, what is power delay profile? It is represented as AC tau and also called the multipath intensity profile. Is defined as the autocorrelation function with delta t equal to 0. So that means basically AC tau is AC tau comma 0. That is time is 0. By putting delta t equal to 0 in the autocorrelation function, we get the power delay profile. So the power delay profile represents the average power associated with a given multipath delay, and it is easily measured empirically. The average and RMS delay spread are typically defined in terms of the power delay profile AC tau as mu Tm is this, that is in the numerator term 0 to integration of 0 to infinity tau AC tau d tau, and in the denominator term also 0 to infinity integration of 0 to infinity AC tau d tau. And sigma Tm is this, that is square root of 0 to infinity tau minus mu Tm whole square AC tau d tau, and in the denominator integration of 0 to infinity AC tau d tau. We now define the PDF PTM of the random delay spread Tm in terms of AC tau as PTM tau equal to basically AC, in the numerator it is AC tau by integration of 0 to infinity AC tau d tau, where then mu Tm and sigma Tm basically represents mean and RMS value of Tm relative to its distribution. Now here, suppose Ts much less than Tm. Suppose Ts much less than Tm. What does it mean? That means the system experiences significant ISI. And another condition, when suppose Ts is much higher than Tm, then in this case there is no ISI is present, or even negligible ISI is present. Next is coherence bandwidth. We can also characterize the time varying multipath channel in the frequency domain by taking the Fourier transform of C tau t with respect to tau is like a random process, and is now defined as CFT equal to minus infinity to plus infinity C tau t to the power minus j 2 pi f tau d tau. And the autocorrelation function is given as AC f1 f2 delta t. It is now defined as expectation of C conjugate f1 t into C f2 t plus delta t. And if we simplify this autocorrelation function, we ultimately get, after some simplification, mathematical simplification, it ultimately we get minus infinity to plus infinity AC tau delta t e to the power minus j 2 pi f2 minus f1 tau d tau. So it is now AC delta f and delta t. Now, what is delta F? Delta F basically this term F2 minus F1, and the third equality follows from the WSS and US properties of C tau t. So, thus the autocorrelation of CFT in frequency depends only on the frequency difference delta F. The function AC delta F delta t can be measured in practice by transmitting a pair of sinusoidals through the channel that are separated in frequency by delta F, and then calculating their cross correlation at the receiver for the time separation delta t. Now, if we define AC delta F equal to AC delta F 0, then AC delta F equal to minus infinity to plus infinity AC tau e to the power minus j 2 pi delta F tau d tau. So, AC delta F basically the Fourier transform of the power delay profile. Okay, and AC delta F, because we know that AC delta F equal to this, that is expectation of C conjugate Ft into C F plus delta Ft is a autocorrelation. It follows that the channel response is approximately independent at frequency separations delta F, where AC delta F almost equal to 0. The frequency BC, where AC delta F almost equal to 0 for all delta F greater than BC, is called the coherence bandwidth of the channel. So this is called the coherence bandwidth, when actually this is frequency BC is called the coherence bandwidth when its autocorrelation function is 0. And this diagram shows the power delay profile. And if we could the Fourier transform of it, now it now becomes like that. Now here uh, in general, if we are transmitting a narrowband signal with bandwidth B with much less than BC, then fading across the entire signal bandwidth is highly correlated. That is, the fading is roughly equal across the entire signal bandwidth. This is equally referred to as basically flat fading. Here, this is shown here. On the other hand, if the signal bandwidth is much greater than coherence bandwidth, then the channel amplitude values at frequencies separated by more than the coherence bandwidth are roughly independent. Thus, the channel amplitude varies widely across the signal bandwidth. In this case, the fading is called frequency selective fading. Okay, so these two, flat fading and frequency selective fading, is very important. And normally in frequency selective fading, there is a chance of ISI. Now, discrete time model. Often, the time varying impulse response channel model is too complex for a simple analysis. In this case, a discrete time approximation for the wideband multipath channel can be used. This discrete time spread spectrum system, this discrete time model is based on a physical propagation environment consisting of a composition of isolated point scatters, which is shown here. In this model, the multipath components are assumed to form subpath clusters. Incoming paths on a given subpath with approximate delay tau n are combined, and the incoming paths on different subpath clusters with delays tau n and tau m, different delays. Therefore, the channel model is modified to include a fixed number n plus 1 of this subpath cluster as C tau t equal to n equal to say 1 to n alpha n t e to the power minus j phi n t multiplied with impulse delay, that is del tau minus tau n t. Now, the subpaths are basically restricted to lie in one of the m time interval. Now, which is basically shown here in this model. This is the discrete time approximation model. Here, these R1 bolt, that means the signals are present. That is a binary indication factor Rn equal to 1 if there is a multipath component in the nth beam and 0 otherwise. If Rn equal to 1, then An theta n, that is A1 theta 1, A4 theta 1, that is An theta n, the amplitude and phase corresponding to this multipath component follow an empirically determined distribution. This distribution is obtained by sample averages of an theta n for each n at different locations in the propagation environment. The empirical distribution of an theta n and am theta m is generally different when n not equal to m, and it may correspond to the same family of fading but the different parameters like Rician fading with different k factors or to different fading distributions altogether, like Rayleigh fading for the nth beam and Nakagami fading for the other like mth beam. Okay. Now, the last topic of this today's discussion, another important thing, which is spatiotemporal model. Spatiotemporal model, that what does it mean? Multiple antennas at the transmitter or receiver are becoming common in wireless systems because of their diversity and capacity benefits. Now, systems with multiple antennas require channel models that characterize both spatial and temporal characteristics of the channel. A typical model assumes the channel is composed of several scattering centers that generate the multipath. The location of the scattering centers relative to the receiver dictate the angle of arrival of the corresponding multipath components. Now consider a two-dimensional multipath environment in which the receiver or transmitter has an antenna array of M elements. The time-varying impulse response models can be extended to incorporate angle of arrival for the array as follows, like following this expression: C tau t equal to n equal to 0 to nt alpha n e to the power minus j phi nt, that is a bar theta nt delta function tau minus tau nt. Now this is a bar theta nt. Now theta nt basically corresponds to the phase shift at the origin of the array, and a theta nt is the array response vector, which is given by following this expression. And here this psi actually represented here xi cos theta nt plus yi sin theta nt into 2 pi by lambda. Now xi yi actually the antenna location relative to the origin, and theta nt is the angle of arrival of the multipath relative to the origin of the antenna array. Okay, so that's all about this chapter, and in the next class we start the performance of digital modulation techniques. Thank you.